Hi everyone, I'm Kexin from Stanford. Today I'll be talking to you about some new research project that we are doing on how to automatically smooth your time series visualizations in your dashboard. I am currently a PhD student at the Stanford InfoLab, working closely with Professor Peter Bayless and Matej Zaharia. I'm really interested in the monitoring space. I think there are a lot of cool problems to work on. So the project that I work on is called Macrobase, which is a system for diagnosing and analyzing anomalies in monitoring. And really excited to be here. This is my first time in Portland and my very first conference talk. Thank you. Yeah. So we're here talking about problems and solutions in monitoring. And one problem that we notice is that the time series dashboards that you guys are reading every day are often noisy. By noisy, I mean sometimes the spikes or fluctuations in the time series can really obscure the overall trend. So here is a plot of my CPU usage over the past 5 hours. Maybe from reading this, I can see that there might be something going on at 4 or 5 a.m., but in general, this is really hard to read. So imagine instead, if I apply some amount of smoothing by a moving average, I would get a much cleaner graph instead, where in this graph, I can see clearly that there are some spikes in my CPU usage, and also overall, my usage has been slowly increasing, which was really hard to see in the original graph. I don't know about you guys, but if I were to get woken up earlier in the morning to see, due to alert in my CPU usage, I probably rather see the latter plot. So this is what we're going to talk about today. How do we automatically generate a smooth plot like the bottom one? This is some ongoing research that's motivated to generate more informative dashboard visualizations. And our idea is simple, that you should consider applying some amount of smoothing to your dashboard visualizations. And in this talk, we're going to go deeper into how to actually set a good default smoothing parameter for your visualizations. Why do I care about smoothing in the first place? Well, we actually did some user study, and it showed that by setting the right amount of smoothing parameter, it actually did make a huge impact on users' ability to identify deviations in time series. So specifically, we saw an up to 38% increase in accuracy and 44% decrease in response time for users to identify deviations in time series by applying smoothing. So we also implemented the above algorithm in a JavaScript library called asap.js that you can try yourself. So going back to this problem of what do my dashboard tell me every day? We see that many dashboards by default just plot the time series as they arrive. We ask, is plotting raw data always the best idea? To illustrate this question, maybe it will be helpful for us to walk through an example where here I have plots for two CPUs, usage of two servers on my cluster. From the time series plot, it might look that these two servers are behaving kind of differently. But it turned out that if you were to perform some amount of smoothing, they actually show almost the exact same usage trend, which was really hard to see in the original plots because they were hidden under the fluctuations. To further illustrate my point how fluctuations can really obscure the overall trend in your visualization, I have another example data set where I have 250 years of monthly temperature data in England. I tried plotting this in Excel, and here is what I got. So on the x-axis, I have time, and on the y-axis, I have the average temperature. Well, in retrospect, actually this plot makes sense because temperature always goes up during summer and goes down during winter. So when I have 250 years of monthly temperature, that means I have 250 fluctuations, which is 250 spikes all compressed together in this visualization. To make sure that I'm just not picking on Excel, I actually tried plotting the same time series on some of other awesome monitoring tools that I've heard of. So, for example, Grafana, Prometheus, and Tableau. Well, don't take me wrong, I totally think these are great tools, but wouldn't it be nicer if my tool can automatically smooth the time series for me instead of having me go through the process of finding a parameter and doing the actual smoothing? And I don't blame the vendors because it is a challenging problem. As you can imagine, the right amount of smoothing probably varies a lot from data set to data set. So how do we come up with some guideline for doing smoothing that would apply to multiple data sets? Turns out that in this case, if we were to perform smoothing on the time series using ASAP, you will see this trend line. Despite some fluctuations, you can see that around 1900, the average temperature started to increase, which is not surprising considering our temperatures are warming right now. So a little smoothing can really go a long way. To summarize so far why it's not always a good idea to plot the raw data, we see that it's really, in many cases, our attention are grabbed by the spikes that's present in time series visualization. So if we zoom into this small area in the CPU usage graph and then expand it, we see that this is essentially a series of fluctuations compressed together. But they're really overrepresented in this final visualization relative to overall trends, which is making it much harder for users to tell what's going on in the system. So far, we've observed that raw data is often noisy. And we've also seen that some amount of smoothing usually helps. So yeah, CAD memes are always good for talks, I figured. So yeah, next we're gonna go into more details on how do we come up with a good smoothing parameter for removing these fluctuations. So the first question that I have naturally is, if I want to do smoothing, what smoothing average should I use? Well, it turns out that moving average are fairly general and they actually work really well in practice. So to be really clear on what I mean by moving average, maybe let's just walk through a really simple example where I have 6 points in my time series and I want to smooth it using a moving average of window size 4. So here I would take the first 4 points in my time series, compute their average, which gives me 2.5, and then I will slide the window forward, compute the average of the next 4 points. And I keep repeating the same move until I reach the end of my time series. And this new 2.5, 3.5, 4.5 time series is my smooth time series. And you notice that we can actually control the amount of smoothing here by changing the window size that we use for our moving average. So overall, in general, if you pick a larger window size that corresponds to more smoothing, if you pick a smaller window size, you'll probably get a time series that's closer to the original one. And it turns out that there's actually signal processing literature that justify that moving average removes this kind of short-term fluctuations very well under many conditions. So it's really a great fit for our purpose, despite how simple it is. So great, now we have a smoothing function. Are we done yet? Well, there's still this question of how much to smooth or what window size should I use to answer. For example, if I want to smooth this spiky CPU usage graph and I apply a small window, well, you see that it helps a little bit, but I still have the remaining spike in the original graph that I want to get rid of. Compared to if I apply a window that is too large, then I get an increasing line. And because I smoothed away some of the spikes that's present in the original time series, I get a little idea on what's causing my CPU usage to increase. And monitoring is all about giving more context and making it easier for users to read. So here's what ASAP comes in. So ASAP stands for making your plots as smooth as possible, which also happen to have initials ASAP, while preserving the long-term deviations. So for the next part of my talk, I'm going to go into more details on what do I mean by smooth and what do I mean by preserving the deviations. So maybe first, let's look at smooth and how would I even quantify smoothness of time series. Here are two example time series. I think the red one is not smooth and the green one is smooth. I hope you agree with me. And so my goal here is to find some statistics that would tell me that the difference in smoothness in these two time series. So the first thing I thought of is taking the mean, right? Average is always good. Unfortunately, they both have mean 0. Well, maybe mean is a little too simple. So let me try something more sophisticated, like a standard deviation. Well, it turns out that they also have the same standard deviation. Well, taking a step back, I'm realizing that the reason why I think these two plots look different to me is because in the first plot, the points are going up and down, while in the second plot, it's a straight line. So if we actually calculate the difference between neighboring points in these two plots, we see that in the first plot, the difference is fluctuating between 2 and -2, while in the second plot, the difference is the same. So if I take the variation of these differences as a metric, then I see that the first plot has a variance of 4, while the second one has a variance of 0 because it's the smoothest possible line. Great, so how do we calculate this point-to-point variance exactly? Simple. Iterate through your points in your time series, calculate the difference between every neighboring points, and then you call the variance function, and you're done. So we already have the first part of the answer. We quantify smoothness in time series using this variance of difference between neighboring points. But so far, ASAP is just telling me to increase window size and decrease this point-to-point variance. But when should I stop? Because remember, the smoothest line is a straight line, but I don't want to make all my metrics a straight line. So here's where the second part comes in. What we're lacking essentially is some kind of constraint in our smoothing that will prevent us from going overboard. So for example, going back to the same CPU usage example, let's compare two smoothing for this time series graph. I personally like the first smoothing better because it got rid of the fluctuations while still showing me the spikes that happened throughout the time. While the second one is not as great because it smooths away more context in the original graph. And the difference between these two is essentially the good smoothing preserves some type of deviation or outlierness in the original plot. So maybe we could just use that as a metric on how to stop us from oversmoothing. It turns out that conveniently in stats, there is this function called kurtosis, which measures exactly outlierness of a distribution or a time series plot. So concretely, high kurtosis means that the distribution that's responsible for generating the time series visualizations have heavier tails and therefore easier to produce outliers, while as low kurtosis means that the distribution have lighter tails and therefore your time series will look more uniform. Let's calculate the kurtosis of these three graphs. So the original one has kurtosis of 4.1. The second one has kurtosis even increased a little bit because I got rid of some of the fluctuations, so it's 4.3. While the third one, you see that the kurtosis decreased to 2.8 because I smoothed away some of the outlierness or deviations that's present in the original plot. And how do I calculate kurtosis? Since it's a standard function, you can just call SciPy kurtosis. Yes, but you can also do it yourself. And here's how you do it. You iterate through the points in your time series, For each point, you get the difference between this point and the mean and raise it to the fourth power. And finally, you divide it by the variance of the time series. And that's it. Cool. So going back to our ASAP statement, so for the first part, trying to make the time series as smooth as possible, we should increase window size to reduce the point-to-point variance. Where in the second part, to preserve the outlierness in the original time series, we should try to preserve structure, by preserving the kurtosis of the original time series. And the nice thing, I accidentally flipped the slides earlier, but the nice thing about kurtosis is that it also tells us when it's not a good idea to smooth. So here is an example time series that tells me the Twitter mentions of Apple on Twitter. And if you compare the original and the smooth time series, the only difference you see is that smoothing is decreasing the spikes in the original graph. So what's different between this plot and the CPU usage plot that I showed earlier? Well, it turned out that this original plot has really high kurtosis. It's like over 700 compared to the CPU graph that we saw has only 4, and the uniform distribution has kurtosis 1.8. So in ASAP, we have this rule kind of that if your graph have a lot of outliers to begin with, maybe it's not a good idea to smooth it. So let's just leave it alone. So congratulations, we've walked through ASAP. So just to recap, ASAP stands for as smooth as possible while preserving long-term deviations. So concretely, that means that we want to minimize the variance of difference between points by adjusting the window size of your moving average while preserving the kurtosis of the original data. As I said earlier, we implemented ASAP as a JavaScript library. So to try it, call asap.js in your front end, and before you plot the data, call this smooth function. So here quickly, I want to show you a demo website that I built using asap.js, where here I show, I have some preloaded time series before and after smoothing. So this is a time series of the taxi volume in New York City. This is the monthly temperature in England time series that I talked about. And this is a time series on of power utilizations in a research facility. So you can also try uploading your CSV and smooth it yourself. Cool. Okay, so as I learned yesterday, ASAP now is also in graphite. So shout out to Bo, who I think is also in Monitorama, who connected ASAP with the graphite API. So he also even included a demo page on how it looks like in graphite. So you should check out his GitHub page if you're interested. Cool. So far we went through how to produce a good smooth plot using ASAP. So specifically by using a moving average to minimize the point-to-point variance while preserving the kurtosis of the original data. So to make sure that we're not just making things up, and smoothing actually do help users in identifying deviations in time series, we performed a user study with 250 people. For each user and each dataset, we show them an example time series. For example, here is a time series of the taxi volume in New York City. And we divide the time series into 5 regions, and we ask them, in which time period do you think a drop in taxi volume happened? In this case, this is the original plot, and the drop happened in region E due to the Thanksgiving break. And we also randomly show the users either the original time series or ASAP smooth time series. And turns out that for this data set, If you show users a smooth time series, users can have up to 28% increase in accuracy and also 44% decrease in response time in correctly identifying this deviation. We tried a similar user study on 5 data sets, and on average, we see like a maximum 38 increase in accuracy, an average of 21, and also a maximum 44% decrease in response time, an average of 24. So this really tells us that sometimes if your data is noisy, you should consider some amount of smoothing. Okay, so far we've went over the problem statement, but I haven't talked about how exactly do I go about and find this window size I want to use for my smoothing. Well, the easy answer is just use grid search and try them all, right? So for each possible window size, I want to transform my time series. I want to check whether the transformed one is smoother than my currently best one and whether it preserves the kurtosis. And after enumerating all possible options, I report the best one. Well, as you see, this is an n-squared algorithm, so it's not very fast. And in case you're wondering, binary search doesn't work for this case because smoothness is not a monotonic function with window size. That means that it's not always the case where larger windows give you smoother plots. So that's part of my job, right? So I'm trying to make it faster by using the fact that at the end of the day, human beings, we are the consumers of these time series plots. So if we can tell the difference, then there's no point doing the computation in a sense. So the first optimization we made is that, well, eventually you're going to see your time series on some kind of end device. And for example, if you use an iPhone, how many pixels does your iPhone have? Well, it turns out for iPhone 7, they have 1,300 pixels. What if I want to plot 1,000,000 points on my iPhone 7? Well, the truth is that given this limited display constraint, only a few window sizes is going to make your resulting time series look different. So our idea here is to pre-aggregate the time series according to your target resolution. And with this, we can save over 3,000x with iPhone 7. So bonus question, since you guys are all smart people, how do we go even faster? Okay, so the answer is just run it on your Apple Watch, right? Because Apple Watch have even fewer pixels, so you get even more speed ups. Great. So the second observation is that as you're in the streaming case where data continue to rise, the update rate actually matters. So here I have 2 dashboards that are streaming. And it might be difficult to tell just from looking at this, but actually one of them is updating almost twice as fast as the others. So the idea here is that even if data arrives quickly, we shouldn't update our dashboard according to the data arrival rate. Rather, we should update it at a rate where humans are comfortable or can make sense of. And the final observation is that a lot of times that time series are periodic, and if they are, we should really take advantage of that. So this New York taxi volume time series fluctuate on a daily basis because according to people's sleep schedule, they take more taxi cabs during the daytime. So given this fact, there is really little benefit in choosing a window that do not align with this period. For example, here I have 2 smoothing, one with a random window of 10 hours. So you see that with this window, I still get a lot of fluctuations in the original plot. Whereas if I smooth it using a day period, then the resulting plot looks a lot smoother. So what we do in ASAP is that we only search for window sizes that correspond to high periodicity in the time series. So altogether, what these optimization does is allow us to run really fast. So we went from the baseline where we can process 0.1 points per second by doing grid search on the original time series to adding in the pre-aggregation by pixel, adding in only search for window size that correspond to period of the data, adding in update lazily, and we get several orders of magnitude speed ups eventually, which allows us to hopefully be able to use it in a real production scenario. So that's all I have for this talk. Hopefully you will start to think about ways to smooth your time series visualizations by choosing some smart defaults. And smoothing empirically can help users better identify deviations in time series and identifying them faster. And if you're interested, please try using our library and tell us what you think. That's it. Thank you. I think I have a few minutes for questions, so please.
Have you considered trying to simultaneously calculate multiple kurtoses at the same time?
You mean, so the question is, have I considered simultaneously calculate kurtoses of at the same time? So are you asking like how to parallelize the search for window size?
Well, you say that you calculate over several sliding windows, but you already have the result of the earlier window size. You could simultaneously calculate 3 and then add 1, and then you can calculate 4 and then add 1 and then calculate 5.
Yes, we haven't done anything really smart about how we calculate kurtoses yet. Right now what we do is we choose the window size, we smooth the time series accordingly, and then we calculate the kurtoses at the end. So the smooth moving average part is O of n, so hopefully it won't be too bad, but I can see that there are room for making that even faster.
With the kurtoses, you said when it got too high, it lost its value. Is there some threshold where it's like a magic number where it says, all right, well, it's 200, this is too much, or is it arbitrary?
Yeah, so the question is that is there a magic number for example, non-smooth time series according to some kurtoses? So the answer is I don't know. In the data sets that I work with, threshold of 10 works pretty good already because so to give you an example, the normal distribution only has kurtoses of 3, so 10 is actually already a lot higher than normal distribution. But I think the specific threshold probably, if you look at, try it on your data, you probably will have a better idea. Yeah.
You said you exploit periodicity in order to cut down the number of points you have to consider when you're calculating. How do you automatically detect periodicity? How do you know that data is a one-day period?
Cool. So the question is, I said I'm optimizing by only search for windows that correspond to period of time, and how do I actually find that period, right? So great question. So we figure out the period in time series by using this autocorrelation. So autocorrelation is this measure of if I shift my time series, I compare my time series from the start to a time series that's shifted by some lag. How similar are these two time series? So autocorrelation will give us like a good indicator of like the window sizes that indicates high similarity. So basically what we do is we calculate autocorrelation for the time series, and if we see a window that corresponds to, only if we see a window correspond to high autocorrelation, we search for that window. And the nice thing about autocorrelation is that it was also originally an n-squared algorithm, but then someone smarter than me figured that they can calculate it using FFT, so now it's n log n. Yeah.
Have you done any research into having different charts on the same dashboard with different window sizes and the benefits or drawbacks of the user experience? Like, hard to understand, or does it work confusing or less confusing?
Cool. So the question is, have I tried having a dashboard with different window size and then tried on users to see how they react? So the answer is, I guess, yes and no. So yes, because when we ran the user study, we not only did I try ASAP, but I also tried some other smoothing algorithms with different moving windows to let users look, and I asked them the same question of identifying deviations in time series. But on top of original and ASAP, I also tried a bunch of other algorithms. But if you go to the website, there is a link to the paper, and in the appendix, we show some of the results where we vary the window size, and we also measure the response time and accuracy for users on these alternative measures. So yeah. Okay, I think I'm almost out of time. So thank you so much for having me here, and I'm here to talk if you're interested. Thank you.